Ever wondered how machines capture fast motion without blur while staying low power and compact? From barcode scanners to AR/VR and industrial inspection, as well as robotics applications such as AMR, autonomous mobile robots, drones, and humanoids, modern vision systems need fast capture, low noise image quality, and efficient size and power. But how can engineers achieve all of this? In this tech guide, we'll explore the onsemi AR0145CS Hyperlux SG image sensors and break down how its global shutter architecture, high frame rate, and low power design make it well suited for next generation embedded imaging. If you're designing vision into a constrained system, or simply want a deeper understanding of imaging, this is a tech guide you won't want to miss.
Step 1. Freezing motion with global shutter plus 120 frames per second performance.
Let's start with the core imaging challenge, and that's motion blur. How do engineers capture fast-moving objects without distortion when both the scene and camera might be moving? The AR0145CS solves this with a global shutter pixel design. This design means every pixel captures light at the same instant. Unlike rolling shutter sensors that scan line by line, the AR0145CS approach freezes motion across the entire frame, eliminating skew and wobble in fast scenes like conveyor tracking or robotics. This enables fast, precise measurements. So with motion blur challenges solved, let's talk speed. The AR0145CS sensor supports up to 120 frames per second at full 1280 by 800 resolution, which helps enable smooth real-time capture of dynamic environments. At lower resolutions, such as Bin 2 mode, the sensor can double this frame rate, delivering even faster scanning throughput for applications that demand it. That combination, global shutter plus high frame rate, means you can track fast events like part inspection, gesture movement, or scanning systems without losing temporal accuracy. So what you get is sharp spatial accuracy and strong temporal resolution, which is critical for machine vision and automation systems that can't afford motion artifacts. Well, we've already solved two major challenges, motion blur and speed, but lighting introduces its own kind of headache. Let's take a look at how to solve unpredictable lighting next.
Step 2. Low noise imaging in both bright and low light.
How do engineers maintain image clarity when lighting conditions swing from dark factory floors to bright outdoor environments? Well, the AR0145CS truly stands out in challenging lighting conditions. The sensor is designed for low noise image performance across both low light and high light scenes, which is essential for systems operating without controlled illumination. It achieves this stability through several on-chip features, including automatic black level calibration for consistent baseline correction, a 5x5 statistics engine that enables auto exposure control across regions of interest, and flexible exposure strategies that dynamically adapt to changing scene conditions. The sensor is also available in both monochrome and RGB CFA color filter array configurations, giving engineers the flexibility to choose the right variant for their application. The result is cleaner image output with reduced grain and improved contrast consistency. This allows the sensor to maintain clarity, whether reading barcodes in dim environments or tracking objects under bright industrial lighting without requiring heavy external image processing. This low noise performance directly improves downstream computer vision accuracy, since cleaner input data means fewer errors in detection, classification, or tracking algorithms. Next, we'll tie this performance to two key embedded factors: size and power.
Step 3. Compact, low-power embedded designs.
How do you bring advanced imaging to devices constrained by size and power, like drones or compact scanners? The AR0145CS is built with this constraint in mind. It uses a 1/4 0.3-inch optical format with 1280 by 800 active pixels and is available in a compact 5.74mm by 4.42mm CSP package. And that makes it a great fit for tight PCB layouts. On the power side, it operates at approximately 150 milliwatt typical power consumption at full resolution and 120 frames per second, which is highly efficient for a sensor in this performance class. Power consumption can also be reduced significantly by lowering the frame rate, making it well suited for power-sensitive applications like drones and other battery-powered platforms where extending runtime is a priority. It also supports low-voltage rails, including 1.8-volt I/O, 1.2-volt digital, and 2.8-volt analog. This helps enable straightforward integration into modern low-power embedded platforms. It also makes it especially well suited for battery-powered systems where every milliwatt of power consumption is critical. So with the AR0145CS, you don't have to trade performance for mechanical or power constraints. Instead, you could still build compact vision systems that deliver high-speed, high-quality imaging.
Step 4. Flexible imaging features and high-speed interfaces.
Beyond raw image capture, modern systems need adaptability. So how does this sensor support different use cases without redesigning hardware? The AR0145CS includes a flexible feature set with MIPI CSI2 output supporting 8-bit or 10-bit data in 1 or 2 lane configurations for high-speed transfer. It also offers windowing, skipping, and pixel binning to balance resolution and speed based on system needs. Additionally, it supports context switching for multiple operating modes, on-chip PLLs for timing stability, and built-in flash control and trigger modes for synchronized imaging. Together, these features allow engineers to tailor performance to the application, whether that involves full-resolution inspection, region of interest scanning, or high-speed tracking with reduced data bandwidth. This flexibility is especially important in embedded vision pipelines where bandwidth, processing load, and latency must all be carefully balanced. Next, we'll wrap everything together into practical design guidance.
Step 5. Implementation best practices for vision systems.
Once you understand the AR0145CS's capabilities, the next step is integrating them effectively into a real design. Start by matching your system architecture to the sensor's strengths. If motion precision matters, enable global shutter mode for distortion-free capture. If power is constrained, consider using pixel binning or windowing to reduce bandwidth and processing load while maintaining useful resolution. Next, use MIPI lane configuration carefully based on your throughput needs. Remember that higher lane utilization supports smoother, high frame rate streaming at 120 frames per second. For embedded control, take advantage of the 2-wire serial interface to simplify configuration and reduce external components. On the system side, ensure proper power sequencing across analog, digital, and I/O rails to maintain image stability. Finally, validate performance under real lighting conditions, both low light and high contrast scenes, to fully tune exposure and noise behavior. Beyond the sensor itself, onsemi also makes it easier to get a working design faster. Development kits, EVKs, and supporting software let engineers build out an entire vision system as a digital twin before committing to hardware, right down to fine-tuning exposure, noise, and imaging behavior in a virtual environment. Once the system is tuned, that same configuration is transportable directly from the SDK environment into the actual embedded system, streamlining the path from prototype to production. When properly implemented, this sensor becomes a powerful foundation for reliable embedded vision.
Conclusion.
The onsemi AR0145CS Hyperlux SG image sensors brings together 3 critical advantages for modern vision systems. Global shutter capture at up to 120 frames per second for motion clarity, low noise imaging across challenging lighting conditions, and a small, low-power design optimized for compact embedded applications. By combining these features with flexible on-chip processing and high-speed MIPI output, engineers can build responsive, efficient, and accurate imaging systems for everything from industrial automation and robotics to AR and biometric sensing. To learn more, visit mouser.com today or click the link below, and be sure to check out our other tech guides, because smart minds never stop learning.